Swayam Prabha. Digital India. Educated India.
Okay, in yesterday's class we defined a black body and then we proposed several arguments. We proposed several arguments to look at the attributes of a black body, namely it is a perfect emitter, there is radiation isotropy of radiation coming out of a black body, that is the intensity is same in all the directions. So it is a perfect emitter in every direction, it is a perfect emitter at all wavelengths, and the enclosure characteristics do not affect the radiation coming out of a black body. It is only the temperature of the enclosure, the temperature of the black body which holds the key to determining the intensity of radiation which is coming out of a black body. And finally we figured out that the radiation strength from a black body is not only a function of temperature, it monotonically increases with temperature, it cannot be an inverse function, it cannot be inversely proportional to temperature. Okay. Then we started introducing solid geometry because radiation is going in all the directions, okay, and therefore it is advantageous for us to use the spherical coordinate system. So from x, y, z coordinates you can go to r, theta, phi coordinates where r is the radius given by root of x1 squared plus y1 squared plus z1 squared with respect to 0 0 0 with respect to the origin, and you can have theta and phi. There are two angles which are entering the problem. One is the zenith angle, how it is displaced from the vertical, okay, that is the zenith angle theta. It is also frequently used in solar energy. People who have taken courses in solar energy or work in solar energy will know that zenith angle is very much useful there, and there is also the azimuthal angle where you are looking at this angle. So the zenith angle is basically with respect to the vertical, the azimuthal angle is with respect to the horizontal. So x, y, z can be transformed to r, theta, phi. Then we saw the difference between the plane angle and solid angle. The solid angle is basically a very important concept to study radiative heat transfer because we are always finally interested in radiation heat transfer between surfaces, whether it is a combustion chamber of an IC engine or whether it is a radiant superheater of a boiler. Basically there are various surfaces, one surface is hot, the other surface is cold. For example, the hot surface is where the radiation is coming out and the cold surface is the surface on which water tubes are there, right, hot water or steam is flowing through those tubes. Then the job of the radiant heat superheater is basically the radiation from one side will heat up the steam or the water which is on the other side. Is that okay? So in all these cases we are looking at radiation heat transfer between finite surfaces. We are not always interested in a small body which is completely intercepted by a hemispherical bucket or hemispherical basket or whatever. Therefore if you are interested in radiative heat transfer between surfaces and these surfaces are a finite area, because radiation has a tendency to spread in all the directions, it is important for us to know the directional orientation of one surface with respect to the other surface. How is the receiving surface oriented directionally with regard to the emitting surface, okay. In order to do this, not only is the spherical coordinate system useful, the definition of solid angle is also becomes imperative or it becomes essential, okay. Just like plane angle is dl by r, the solid angle is dan by r squared. Under the spherical coordinate system we just broke down dan into r sin theta d phi into r d theta, then the d omega became sin theta d theta d phi, okay. R square and r square get cancelled and the omega for a hemisphere became 2 pi radian, steradian. Why are we not talking about sphere and we are always talking about hemisphere? Yeah, because we are always interested in the surface. So radiation from a surface too, but this is not the be all and end all of the whole of everything. For example, if it is radiation from the atmosphere, if you consider a volume, then radiation will travel in the upper hemisphere and the lower hemisphere also. So when we come to radiation in participating media, particularly with radiation in the atmosphere and so on, it need not be radiation in the atmosphere, it can be radiation from the combustion gases in a combustion chamber. Once you have water vapor and carbon dioxide, they won't keep quiet. Carbon dioxide you also know is a culprit for is a greenhouse gas, is a culprit for global climate change and all that. So if you have carbon dioxide in water vapor, then the arguments will slightly change. instead of talking about hemisphere we will talk about full sphere, okay. But the first part of the story is we want to calculate radiation heat transfer between surfaces, right. So the surfaces are at different temperatures, they are characterized with different paints whatever, they are oriented in different directions, there can be several surfaces. What is the net radiation heat transfer between any two surfaces? This is the fundamental engineering question which we want to answer. A slightly more complicated version of this is, apart from radiation there is also convection and conduction which are taking place, so it becomes a truly multi-mode heat transfer problem. Under these conditions, how do we handle radiation, either when it is alone or when it is in conjunction with other modes of heat transfer? And we have already seen that even at low temperatures radiation can be significant if natural convection is present. Therefore we focus on radiation between surfaces, alright. Now please take down this figure, this is crucial for you to understand the concept of radiation intensity which is defined by I, right, which I am going to define in the next few minutes. Now this is basically the dA1 is the emitting surface, is the surface which is emitting the radiation, it is elemental, right, dA1. There is another elemental surface, so this is given in red or orange color, this is given in yellow color, so that is dAn. dAn is elemental surface which is intercepting the radiation from dA1, okay. So the radius, if you join the center of the dAn and the center of dA1, it is r. In principle if you join any point on dAn to any point on dA1, it should also be very close to r, because dA1 and dAn are after all infinitesimally small surfaces, okay, otherwise the analysis will cup, okay. It is r, then the other two angles are basically the zenith angle is coming, so this angle is theta and this angle is d theta, and then if you project it onto the horizontal plane, so this is d phi and d phi or d phi and this is phi, alright. Now theta can vary from 0 to pi by 2 for the hemisphere, theta can vary from 0 to pi for the full sphere, we are looking at hemisphere, so it is up to pi by 2, and the azimuthal angle is 2 pi, 360 degrees, okay, it can be 2 pi. So the title, the caption for this would be emission from a differential area dA1 into a hypothetical hemisphere centered at a point on dA1, which is at a radius, and the radius of which is r, that is a figure caption. Now with this in background we will introduce a quantity called radiation intensity. So this becomes essential radiation intensity is given by I, the subscript lambda denotes that it is a spectral quantity, that it is concerning the radiation intensity in a small wavelength interval d lambda about lambda, that is why it is lambda. E denotes it is emission, it is applicable for reflection and other things also, but we have to start somewhere, right, so I will consider emission, okay. So this is called the spectral radiation intensity. In conduction and convection heat transfer we have Q, flux, correct, flux is watts per meter square. When already we have watts per meter square, where is the need to introduce another intensity? Why do you think radiation people have introduced this? Already there are so many things to bother us, why can't we just work with flux? Why did people deem it fit or necessary to introduce a new quantity called lambda or called I? That can be handled by, yeah, you can proceed further. You want to have a quantity which can vary with wavelength, right, so that is spectral, that is okay, but why is intensity spectral? It is basically there is also direction involved. The answer to this question is, it becomes necessary for us to introduce a spectral radiation intensity because radiation falling on a surface can come from all possible directions. The radiation emitted from a surface can also be in all possible directions. Therefore it is important that the directional nature of the intensity of the radiation is taken into account. the flux as such is it's very difficult if you work with watts per meter square, okay. Therefore, you define a radiation intensity which takes care of this directional effects, and in conjunction with your definition of solid angle and spherical coordinate system, it becomes much more easier and convenient for you to handle radiation heat transfer problems. Therefore, the first step in technology is to define the radiation intensity, okay. So, the radiation intensity can be defined as okay. So, please take it down and tell me what the units of radiation intensity are. I will define it formally, I have defined it mathematically, I will define it formally. So, the spectral radiant intensity, of emission given by I lambda E is the rate at which radiant energy is emitted per unit, okay, you can take down the spectral radiation intensity of emission given by I lambda E is defined, what did he say first? Is defined as the rate at which radiant energy is emitted rate at which radiant energy is emitted per unit area, radiant energy is emitted by a surface, per unit area normal to the surface, rate at which radiant energy is emitted, what did he say, by per unit area normal to the surface in the direction theta phi, per unit solid angle d omega about theta phi or around theta phi, whichever way is better for you, around theta phi in a unit wavelength interval d lambda about lambda, in the unit wavelength interval d lambda about lambda. Yeah. Now you taken down the definition, you also have seen the mathematical form of this, you also have the figure accompanying this. Please see if all this makes sense. Okay. So, the spectral intensity of emission is the rate at which a particular area is emitting radiation, that can be dA1. So, it is a flux quantity per unit area normal to this in the theta phi direction. The theta phi direction is given by this. So, that is why I have dA1 cos theta, so that I take care of, if this is the area, I take care of this, because this surface will not know dA1, it will see only the projected area. Please watch carefully, this is the receiving surface, it does not care about dA1, it always cares about dA cos theta. That is why in a solar collector also, depending on the latitude and all this, if you want to track the sun, you want it to be normal, so that you capture the maximum rays, correct. So, it is the amount of radiation which is leaving this, amount of the rate at which radiant energy is emitted by this area per unit area normal to this in the theta phi direction about a solid angle, about an elemental solid angle in the theta phi direction, okay, per unit wavelength interval d lambda about lambda, okay. So, the units will be watts per meter square per micrometer per steradian. We can work with this further. Now let us qualify this. So I lambda e must now be a function of lambda, correct. Then very good, that is all. Temperature is not coming, I do not know, I mean that comes later, that story I do not know now. Okay, I lambda is that all d omega. Okay, let me say any problem?
No, where is there any variation with phi? You defined I lambda as a function of lambda theta and phi. In that expression there is no variation with phi.
What is d omega? Sin theta d theta d phi. Solid angle will depend on phi, right? Okay, fine. So now what are the units of dq lambda? What per meter square per micrometer? Is it correct? It's correct, it's correct, it's correct. Okay. I'll erase this. Okay, so what will be the units for this? Should be dq lambda into d lambda, is it? Or you won't get confused? The variable is d lambda. It's okay? Okay. You should not get confused with the notation. Now this is a very important equation. Equation number 6 is very important. Don't get worried. So we will encounter double, triple integrals in this course, but I will make it manageable. Don't worry. Huh? I have not done any magic so far. I have not introduced anything which you have not studied so far. Okay. So, the importance of equation 6 is as follows. If I know what I lambda E is, yeah, yeah, oh, okay. The importance of equation 6 is as follows. If somebody gives me a distribution for I lambda E, it is possible for me to integrate and find out what is the value of Q. So, it lets me calculate the Q, between surfaces provided I lambda E is known. But who will give me I lambda E, that is a separate story. Somehow if somebody gives me I as a function of lambda, theta and phi, it could also be some other variable like temperature, I do not know as yet. If somebody tells me I lambda E with, so we have a mathematical framework for converting I to Q. Please remember that the Q is based on the actual area because Q has got the units of watts per meter square, but I is based on the projected area because it is dA1, you have to get dA1 cos theta, because I lambda takes care of the directional effects, okay. So, while I is based on the projected area, Q is basically based on the actual area. Therefore, this is a fundamental expression. So, this is valid. So, this is valid regardless of whether you have emission, reflection or incoming radiation, okay. The incoming radiation is called irradiation, okay. So, now we will write a general statement. Therefore, I can say that equation 6 is a generic expression to convert I to Q. It is applicable for radiation which is emitted from a body, or radiation which is incident on from a body, or radiation which is reflected from a body, okay. Now, we will get back to our black body and see how we can define the emissive power of a black body based on the mathematical framework we have proposed here, okay. And then we will come to a stage where if you know what I lambda E is for a black body, it is possible for you to calculate spectral flux, directional flux, total flux, all these things. And then we will see how the story started about, that is the quest for finding I lambda E. So many scientists have found, first they figured out the incorrect distribution, Rayleigh and Jeans, and finally Planck figured out the correct I lambda E. If the correct I lambda E is put into this framework, then automatically the Stefan-Boltzmann's law will emerge, and if I lambda is differentiated, you get the Wien's displacement law. All the fundamental laws will come from one fundamental expression for I lambda E. So, the I lambda E, the search for I lambda E produced so many Nobel laureates, okay, and so many physicists miserably failed. Celebrated physicists, Rayleigh, Jeans, so many British physicists miserably failed, and they try to hold on because they try to explain I lambda E from classical physics. The quantum jump came when Planck used the quantum hypothesis to derive the correct, to hypothesize or propose the correct distribution for I lambda E. Even today we cannot say that this is the only distribution which is correct. It may be disproved later on, but the arguments seem to be sound, and it is the only distribution which agrees with experiments. Therefore, the Planck's distribution must be correct till it is found incorrect. Okay, boundary layer theory is correct. It has a shelf life 1905, 105 years. It is useful. It has been useful, but it does not mean that life ends with boundary layer. There may be somebody who is much smarter than Prandtl who will propose, and if everybody accepts, then in 2030 BTech students will take instead of Bondier theory they will learn that, but it never happened. From 1907 5 everybody is learning the same thing. My teachers learned the same thing, I learned the same thing, I am teaching the same. That means it has withstood the test of time. Certain things are timeless. So boundary theory is one, Planck's distribution is yet another. Okay. Now we will look at the emissive power from a black body. Okay. So E B lambda, I use the expression E for the emissive power. E B lambda is basically given by 0 to pi by 2. I will keep using this throughout this course. This refers to the integration with respect to the theta, this refers to the integration with respect to the phi or phi. Okay. So I lambda E what is equation number 7? It is called the spectral hemispherical emissive power. Okay. Why is it spectral? Because it is still a function of lambda, I have not integrated with respect to lambda. Why is it called hemispherical? I have integrated with respect to a hypothetical hemisphere by doing two integrations, integration with respect to theta and integration with respect to phi. Alright. What should be the units of this guy? What are the units of EB lambda? Watts? Watts per meter square per micrometer. Meter is too big for us, do not say sir we will make it watts per meter cube. Meter is a unit for length, micrometer is also a unit for length. So we may be inclined to put watts per meter cube, it will give some silly numbers, it will give indecent numbers. So we want to put watts per meter square per micrometer, right, because meter is too big for us. Now I think we are all sleeping. I told so many stories about a black body. Black body is a perfect emitter, it emits the same in all the directions and all that. Why should the I be inside the integral? Pull it out of the integral and simplify the expression, please do it. A black body is a diffuse emitter, that means the I lambda E is not a function of theta and phi. Yesterday I told you stories, in all the directions it is the same. Why should that stupid I lambda E be inside the integral sign? Pull it out, just do the integration with respect to the two angles. Okay. The black body is what is the meaning of this? That is okay. Therefore is it correct? Okay, now do the integration. So what are you doing? What are you? correct? Huh? Sin 2 theta is 2 sin theta cos theta. I didn't mix up, right? Okay, we can derive it from first principles. If I have any doubt, how do you check? I will take for 90 degrees, 2 theta is 90. If from the calculator we can check. After doing many things, you will get a doubt whether sin 2 theta is 2 sin theta cos theta or cos 2 theta is 2 sin theta. We can check it out. Now, finally, EB is equal to okay. Now, the beauty is with after having defined the plane, after having defined the solid angle, after having introduced spherical coordinate system, and after having introduced I lambda E, we have an excellent framework with which we can calculate the flux. The quantity of engineering interest is all these quantities are on the left hand side of the equation, whether it is EB lambda or EB. Right side is I, right side is physics, left side is engineering. The right side, whatever those physicists, whatever they have figured out, we take that I and do all these integrations and get the spectral quantities or the total quantities. So, this is basically total hemispherical emissive power. Total means the direction is the integration is with respect to the wavelength. Hemispherical means the integration is with respect to the angle. So, the total hemispherical emissive power or simply the total emissive power is 3 integrations performed. So, you must try to now, having already studied the Stefan-Boltzmann's law, you must remember that in Stefan-Boltzmann's law 3 integrations have already been done. I do not know how many of you are aware of this. The Stefan-Boltzmann's law has 3 integrations already, 3 integrations are incorporated, theta, phi and lambda. The fundamental, the primordial relation which leads to the Stefan-Boltzmann's law is the fundamental I lambda which a black body is supposed to emit, which can be verified by experiments and which has been proposed by theory, that we are going to see in the ensuing classes. But now we will do some warming up exercises. We will do 1 or 2 simple problems relating I and Q and solid angle and all that, and from tomorrow's class onwards I will start with radiation intensity, radiation pressure, how first they figured out the incorrect distribution, and that will take some 3-4 classes. Okay. Now let us solve some 2 problems. So 2 important points you have to note. If you look at radiation and heat transfer between surfaces, we are talking about hemisphere and not about sphere, point number 1. Point number 2, surprisingly the result has pi and not 2 pi. Okay. Fine. So problem number 2 is it? 3, good. So we are looking at a simple problem whose solution will reinforce the basic concepts which we have studied in the last two classes. So the figure is like this, please take down this figure. There are two elemental surfaces A1 and A2. The areas of A1 and A2 are given on the blackboard. A1 is 2 into 10 to the minus 4 meter square and A2 is 7 into 10 to the minus 4 meter square. This is the fellow who is emitting and this is the fellow who is receiving. So the power of emission from this surface is given in terms of V is 9 into 10 to the power of 4 watts per meter square. That micrometer business has been taken care because one integration with respect to lambda has already been done. So what is the question now? What should be the question? What is the what is the radiation or the heat flux due to radiation which is correct, which is falling on or which is received by A2, that is a simple. So it is basically a geometric problem. Though it is a thermal problem, we have broken down the thermal part by already declaring 9 into 10 to the power of 4. What should be the temperature and what should be the characteristics of A1 to ensure that 9 into 10 to the power of 4? Right now we are not discussing. We are now discussing only the geometric aspects so that our concepts are clear. Okay. Anyway, we need to have a problem statement, right? Consider a small surface of area A1. Consider a small surface of area A1. I am not giving the values because they are all on the board. Consider a small surface of area A1 which emits diffusely. Diffusely means it is the same in all the directions. Which emits diffusely with a total hemispherical emissive power, or you say with an E of 9 into 10 to the power of 4 watts per meter square. Please remember E is total hemispherical emissive power. Okay, with a total hemispherical emissive power of capital E is equal to 9 into 10 to the 4 watts per meter square, full stop. Question is, what is the rate at which a small surface A2, what is the rate at which a small surface A2 with an area of 7 into 10 to the minus 4, or you need not take that 7 into 10, it is already given on the board. Rate at which a small surface A2 oriented as shown in the figure, oriented as shown in the figure. So what is the rate at which a small surface A2 oriented as shown in the figure intercepts this radiation, intercepts, that is receives, intercepts this radiation. Okay. So you have to look at the quantities relating I and Q. I will tell you briefly the steps involved. You have to look at the relationship between I and Q. You must invoke the definition of solid angle. Please do it. Correct? Right, it is diffuse. If it is diffuse, I know that the relationship between E and I is E is equal to pi times I. Okay. Okay. E, I am using the terminology IE because to denote emission. So I will put it as equation 1. Therefore, IE okay, that is the first step. What?
By deriving EB is equal to pi IB, integrated from 0 to pi by 2. Here it integrated, I mean, it limit over the whole sphere.
No, it is only surface.
Only one small surface. In previous derivation, we just considered only.
No, I am not considering anything below. It is only the okay.
You said one integration has been done already. 3 integrations are done. Because it's watts per meter square.
No, that is for the overall E.
So the E given here, that has 3 integrations.
No, here it is done. but still it is directional. It is diffuse, that is the point. It is same in all the directions, but when we invoke the solid angle, we take at the particular I in the particular direction. What is the confusion? What you are saying is correct, already integrations were done, otherwise we will get per micrometer this thing and all that. Okay, but it is diffuse, so it is the same in all the directions. You just watch me solve this. So d omega is that right? The solid angle is A of the receiving area multiplied by the cos theta 2 divided by r squared. This r, if you do not like this, okay. So this is 7 into 10 to the minus 4 into point cos 30 divided by 0.4 whole square. Deepak, that is the 2.866 into 10 to the power of 4 watts per meter square per steradian is the uniform diffuse radiant intensity which is going in all the directions. Okay. If it were to be intercepted, watch carefully, if it were to be intercepted by a hemispherical basket which replaces A2, then that 9 into 10 to the power of 4 watts per meter square will be the final value. But unfortunately this A2 is only a part of that hemispherical basket. Outside this A2 and whatever is part of the basket is outside the A2 is also equally entitled to receive this radiation. Now it is clear? Fine. Now IE Q by A1, I am freely using A1 and A2 instead of dA1 and dA2 because in the problem I told the A1 and A2 are elemental. By elemental I mean that between any 2 points the angle is the same and the radius is the same, but I can make A1 and A2 finite areas and I can give assignment number 2, it is possible for me. So you have to subdivide it into various areas and then use coordinate geometry, find out the r, find out the theta and then integrate it. That is how we do when we solve engineering radiation problems. That is what this Fluent also does, S2S model is there. How many of you use Fluent? There is something called S2S, surface to surface model for radiation in Fluent which does that, okay. So now 2.866 10 to the power of 4 okay. So it receives 0.011 watts, okay. We found out the answer, everybody got this answer. But if you want to have a real physical field, if you want to have a more comprehensive picture of what the state of affairs is, then you will have to see what is the Q total which is coming out of the surface. What is the Q total from A1? What is it? 9 into 10 to the power of 4 into what is the area? 2 into 10 to the power of minus 4, 18 watts. Because in between it is vacuum or air or whatever, there is nothing which absorbs the radiation, okay. Therefore the total flux or the total radiation energy which is coming out of A1 is 18 watts. Out of 18 watts only 0.011 watts is intercepted. So fraction intercepted is how much? 0.011. How much is it?
6.1 into 10 to the power minus 4.
Minus 4 or 3? Okay. Okay. Now A2 cos theta 2 is the area which is oriented normally to A1 and divided by 2 pi r square is the total area of the hypothetical hemisphere of which A2 is a part. Now you can see that this will be tantalizingly close to that 6.1 into 10 to the power of minus 4. See that? How much is it? To cut a long story short, if A2 were to be a hemisphere, it will capture all the radiation which is emitting from which is coming from A1, but since it is a small area, it receives only that much amount of radiation, and in order to quantify that we put solid angle, this thing, and definition of I lambda in and all that. This leads us to the concept of what is called view factor or shape factor, which we use in radiation. How much is the second surface oriented with respect to the first surface? If the second surface were to be a hemispherical basket, it will have a view factor equal to 1. So the ratio of its area to the area of the hemispherical basket will give an approximate area of the view factor. Of course the view factor is a little more complicated, theta 1, theta 2 and all that will come, and you have to subdivide the A2 into several areas, and each of these areas may have a different elemental view factors, but this gives you broadly an idea of what the view factor is all about. Therefore the orientation of an object with respect to the orientation of the object which is receiving the radiation with respect to the object which is emitting the radiation is critical in ultimately deciding how much of radiation will be eventually intercepted by the object number 2, right. We will do one more small problem, that is how much is the, and we will do a small problem in tomorrow's class, how much is the energy intercepted between 30 degrees and 60 degrees, and phi is equal to 0 to 45 degrees and so on, so that you get comfortable with those integrations. And now what is that I? What is I is also the fundamental question in philosophy. So radiation philosophy are always, in fact originally physics processes are called process of natural philosophy, right, and all this. Okay, what is the I? Okay, just like Ramana Maharishi you have to say who is this I. Yes. Now I will say instead of who is this I, we will say what is this I, how to find out this I. Okay, in the next few classes we will go through some very tricky and rigorous mathematical derivations to find to get the right distribution for I. Okay, tomorrow please come at 8 o'clock. Okay, thank you.